Alright, so let's go back over quickly. Last time we started with this. 4 different types of Fourier transform, inverse transform, 4 different sets of equations, all very closely related. Here we have the representation of signals of the 4 different types: continuous or discrete signals, and periodic or aperiodic. When we look at the corresponding transforms, here we have periodic discrete transform, here we have periodic continuous transform, here we have discrete aperiodic transform, and here we have the continuous aperiodic transform. Okay, we talked about the relationship between Fourier series and Fourier transform, that you can change a Fourier series into a Fourier transform by adding delta functions. Impulses at the frequencies where the Fourier series exists. Okay. And here we have the Fourier series, here we have the Fourier transform. The impulses are represented by arrows. Alright, so now we got to the new stuff, and let me go back to my commentary. Alright, so this is a key slide, and it's worth thinking this through. This is a very rich diagram and can take a lot of thought. Different Fouriers, so I just call them different Fouriers, different Fourier pairs. I could say different Fourier pairs, probably that would be the best way to say it, are related through 2 different types of limiting process. All right, here we have, for instance, longer and longer time interval. Okay, longer and longer time interval means smaller and smaller frequencies are required. All right, so I showed how you can have a finite. Where did I show that? It was over here. You can have a signal on a interval, and the very long frequencies, the very low frequencies, you don't need to worry about because they're close to constant. However, if you have longer and longer intervals, you can have a lower and lower frequencies. Like if I have a interval that stretches across this page, right? Then if I do something very, very slow like this, this is a full period, and I would need to include that in my Fourier series, whereas I wouldn't need to include it in the Fourier series for a shorter interval. All right, so that's one type of limiting. That's one type of limiting process: longer and longer time intervals. The other type of limiting process is the samples become closer and closer. Right? If you have discrete samples getting closer, so that's this n goes to infinity. Right? You have samples that are closer and closer, so you need higher and higher frequencies, because if you think about the aliasing, the aliasing, if you have, so I showed that picture here with aliasing, not a very good picture, but this curve here and this curve here have the same samples. But if I make my samples closer together, I'm going to need to use higher frequencies before I start aliasing. Okay? So those are the 2 types of limiting process: higher frequencies and longer time intervals. And these are processes whereby you go from what you could call simpler representations to more complicated representations. Right here, the time interval goes to infinity, goes from the periodic continuous time and this aperiodic continuous time, and that's this one is a series. This is an integral, so it's more complicated. The more and more closer and closer samples is what's called interpolate. And that goes from this periodic discrete time to periodic continuous time, or and then this also is another way of doing it, that you're taking more and more samples. That's the same thing as closer and closer samples, basically. Right? So that's how you go from what you might call a simpler Fourier representation to a more complicated. So it goes from discrete to continuous. It also goes from periodic to aperiodic on an infinite interval. Okay. All right, now he's using an example of the so-called 10 function. This is also used in the homework, And the next two slides give you a fancy way of computing the Fourier transform. This is actually the convolution of this signal with itself. You can see how that works, that as you slide this signal relative to this one, you're going to start at 0 and then it increases and then goes down again. So this is, you could just compute this Fourier transform directly. So he's doing that in another way. Right, so suppose you take this signal and you make it periodic in time. Now that's the same thing as considering the signal on a finite interval. Right, because we know that if we take finite Fourier series, essentially then you're creating a periodic representation. Right? So here we have a periodic continuous signal, but we're considering it as a signal on the infinite domain. So you could obtain this infinite series of triangle pulses by convolving it with a delta function. So let me show you how that works. If we take the convolution of two functions, and you remember this whole sliding example of convolution. Basically, you take a copy of t and slide it across f, and then multiply the overlap, or integrate the overlap. All right, so you have this integral of f of tau times g of t minus tau d tau. All right. Now what happens if g is a delta function? Right. Now remember, the point that he makes is that f of tau convolved with g of tau is a function of t. But I want to put the t here to indicate that both of these f and g are functions of t. The result is also a function of t. Right. You can see that tau is the integration variable, so it integrates out, but t remains. Right. So if I put delta in for g, I'll get this expression here. First of all, I'll do this with an unshifted delta. Now what happens when you do this? We know that the delta function is 0 except when the argument is 0. So this is a function that's 0 except when t equals tau. Right? Now you should think of a delta function as an infinitely large spike located just very close to t. Now if that multiplies f of tau, it's going to pick up the value of f of t at that point, and the other values of f don't matter at all. So I'm just going to get f of t times the integral of the delta function, which is 1. All right, so if I take f of t convolved with delta, I'll just get f of t back again. So delta is kind of like an identity. Now, just as an aside, you might ask the question whether the functions with the operation of convolution form a group, and the answer is no. First of all, because delta is not technically a function. Second of all, there's no inverse. In fact, there's something called a semigroup that applies here, but I don't want to get into that. But, it is an identity, but there's not a group here. All right, now suppose now we take delta for a t minus kt, so that's shifted delta. Now this delta is non-zero when t equals kt, so this delta is shifted over to the right by kt. Now if you do the same convolution, now when tau is t minus kt, then the integrand is non-zero. Right? Now again, the delta has support exactly when tau equals t minus kt. So the value of f at that point is f of t minus kt. I can pull that out, and this integral just becomes 1. I get f of t minus kt. So the way to shift f using convolution is simply convolve with a delta function. Now why do we want to convolve with a delta function? Because if you convolve in the time domain, that's the same thing as multiplying in the frequency domain. We've seen that the Fourier transform of the convolution of two functions is the product of the Fourier transforms. So let's go back here and see if we can pick up from here. All right, now let me go back here to give some background before we continue. Where are we going with all of this? What we want to answer is the question, what is the Fourier transform of a periodic signal? And I should call this continuous signal because we're looking at continuous signals. All right, now the answer is, I'll give you the answer and then we'll go through the derivation. The average answer is the Fourier transform of a periodic signal with period t is an infinite sum of impulses on frequencies that are multiples of 2 pi over t. So a periodic signal gives me a discrete Fourier transform. Now, the Fourier transform of the periodic signal is closely related to the Fourier series of the periodic signal. The Fourier transform of a periodic signal can be found directly from the Fourier, from the Fourier series of the signal, okay, on one period, by sampling at frequencies that are multiples of 2 pi over t, and then multiplying by 2 pi over t. Okay, so we'll see how this works. That if you look at periodic signals as functions on an infinite domain, you can write this as a sum of impulses, and the impulses are at frequencies that are equal to the frequencies that are used in the Fourier series. Right? So here we have some technical details. So that's what we just talked about. That you can get the Fourier transform of a signal by convolving it with shifted delta function. So if we get a bunch of shifts, if we get a periodic extension, we want to shift the triangle wave by several values, right? To get this periodic shift, I want to shift it by delta functions so that I create an infinite number of copies of this triangle wave. Right? Here he puts plus 4k. You could put minus 4k. It's the same thing, right? Because he's going from minus infinity to infinity. So the strategy is once we have this, then we can take get the Fourier transform by taking the product of the Fourier transform of my single triangle wave, which he computed earlier, times the Fourier transform of this series of pulses. Then he finds the Fourier transform of the series of impulses in a very nice way. All right. What he does first is says, okay, now since this is a periodic function, I can find the Fourier series for this. Okay. To get the Fourier series is not so difficult. I just take one interval, say from minus t over 2 to t over 2, and integrate the delta function times the, well, you know the expression, it's up here. It's this one up here. Sorry, continuous time. So you just do it, you integrate it times this complex exponential. Now remember, delta function has a support only when t equals 0. So I'm going to pick up the value of e to the minus j2 pi over t kt when t equals 0. When t equals 0, this value is what? Think about it for a moment. What's the value of e to the minus j times 0? That's right, it's 1. Okay, so in fact, ak is going to be 1 over t for any value of k, because this exponential is always 0 when t equals 0. Okay, so that gives me the Fourier series for a delta function. And then we use this neat fact up here, where we talked about here that the Fourier series can be converted to a Fourier transform simply by adding pulses where you have the frequencies. And that's exactly what he does here. All right, so he changes these frequency values into pulses and multiplies by 2 pi, so he gets 2 pi over t here. Actually, he multiplies the 1 over t by 2 pi. All right, so now we have the Fourier transform of a periodic signal. Now, I just added some commentary here that this response makes sense, that I'm only going to get frequencies that are multiples of 2 pi over t. Why is that? Because if I took the Fourier transform expression for this, it's going to be an integral from minus infinity to infinity. And it's going to involve, right here, the function times e to the minus j omega t. Now, if omega is not a multiple of the base frequency, what happens when you take e to the minus omega t times this? Well, it's going to oscillate. And it's going to oscillate randomly relative to the sampling. So that oscillation, when I add up the samples, it's going to cancel. And the cancellation makes it to be 0. Since it's 0, it's not going to have any value. So it makes sense that only these frequencies are going to contribute. So that's one way of looking at it. Another way of looking at it is you take sum the Fourier transforms of the shifted delta functions. Now, the Fourier transform of a delta function is the constant function. We just saw that before for Fourier series. It's the same thing for Fourier transform for delta function. You just plug delta in for in the Fourier transform formula, and you get 1. Or is it 1 or is it a constant? Just plug it in up here. Okay, if I plug the delta function in here, you're just going to get 1, right? Because when t equals 0, this is going to be 1. Right? So that means that the Fourier Fourier transform of delta is 1, and then if you shift a function, that multiplies the Fourier transform by e to the j omega. Right? So if I shift by k times t, I'm going to multiply this 1 by e to the j omega kt. Now, if you sum this up for any value of omega, you're going to get a geometric series. And that geometric series, if you think about it, the omega is going to go round and round the circle, and these values are going to cancel unless omega is a multiple of 2 pi over t, in which case you're just going to get 1 on for each term, and then you get an infinite sum. Okay, so that makes sense that the Fourier transform is going to be 0 unless omega is a multiple of 2 pi over t. All right, now if we go back to slide 16 here, remember what I said previously is that to get the Fourier transform of this periodic function, I simply need to multiply the Fourier transform of x times the Fourier transform of the impulse train, which itself is also an impulse train. And this one was computed earlier, I think in slide 15. And so you're simply multiplying this Fourier transform, which is the Fourier transform of x, times the impulse train. And what that does is it simply samples. It samples the Fourier transform at various points. It samples and then also multiplies by pulses. But basically, it's just sampling the Fourier transform of the original triangle function. Okay, let me stop there, and we'll continue in the next video. Thanks for watching.